So we're going to learn about, in this next section, area and the definite integral. And what was it we just learned about? Yeah, so what's the difference? Well, that's what we're going to find out, I guess. So yeah, before we had a little indefinite here, right? Now it's definite. That's going to be something different. But the big key, we start out by learning about area. Now, what do we know about area? Well, I guess we know some formulas from geometry class from a long time ago, right? So we'll see what we're doing here. Here's an area problem for you. Find the area under this curve above the x-axis. Under that curve and above the x-axis. This is the type of problem that motivated a lot of the ideas behind calculus. By the way, what does this curve look like? It's a parabola, right? Maybe I could do a little Calc 1 with you, and we could learn a little more about the parabola. Let's take the derivative. What do we get? Okay, so 4 minus 2x, or negative 2x plus 4. And then when you take the derivative, after you do that, sometimes we set it equal to. Why would we do that? Yeah, we might want to find the critical point. So to get the critical point, I'll say 0 equals 4 minus 2x. So 2x is 4. So x is 2. So somehow, x equals 2 is what's called a critical value. It's an important value. The thing that's important about it is that the derivative is equal to 0 there. So what's that mean? If the derivative equals 0, what does that mean? Well, if you have a constant, the derivative is 0, right? So that's one thing that's true. If I have a constant, the derivative is 0. But if the derivative is 0, this is not a constant, this is a parabola. So what is it telling me? Well, maybe the thing to do is to sketch a graph. So give me some ordered pairs on this thing. Like if I plug in x equals 0, I get y equals. Okay, so this goes through 0, 0. Give me another point on this thing. 1 comma 4 minus 1 is 3. Yeah, so 1 comma 3. It's right there. How about 2 comma... Yes, 2 comma 4. And somehow I said that's an important point. That's a critical point. Right? 3 comma what? $12 minus 9. Our arithmetic needs some... All right, no, here we go. 3 comma 3. Notice it's the same as 1 comma 3, right? When you have a parabola, you get real nice symmetry. And actually, what else do we have? How about this point here? 4, 0, right? And actually, I could have known that if I had factored the thing. It would have been x times 4 minus x. And you could see you have zeros both at 0 and at 4, right? So the graph of this parabola looks like this. Okay? And so, by the way, what did the critical point give me? The vertex, because that's your maximum. Because what's the slope of a tangent line through that point? It'd be 0. It'd be horizontal, right? So it'd be 0. So you have the importance of the first derivative is it can help you find critical points, which are going to be maximums or minimums. And if you did y double prime, which we didn't, you would have gotten negative 2. Concave down, so that's how I know it's a maximum. There's a lot of stuff here from Applied Calc 1 right in this problem. Okay, what am I trying to do? Find the area under the curve and above the x-axis. So we're trying to find all this area in here, right? So if I redraw the picture, here's your parabola. I'm trying to find the area of that shape. And if you look in your geometry book, you probably won't find a formula for the area of that shape, right? That's no good. Now, if I said, same problem, find the area under, I don't know, y equals 4. Oh, no, let me not do that. Let me not do that. Scrap that. Question is, how do you do it? How do you find the area? What's that? If it were half of a circle, I'd say that's awesome. I don't know. Does it look circular to you guys?
No.
You're thinking it doesn't?
I don't know.
You have to what? Integrate. Well, okay. Why? You learned this at some point. Somehow, this antiderivative stuff that we were doing has something to do with finding the area under this curve. What the heck why would that be the case? That's actually a remarkable theorem. It's called the fundamental theorem of calculus. And that's what we're going to cover next time we meet. That somehow, all this antiderivative stuff we did in the first half of the class today has something to do with finding the area under the curve. Now, I might not be able to find the area under the curve right now with the tools I have, but I can approximate the area of the curve in the following way. I'm going to use rectangles. Now, what do I mean by this? I'm going to draw some lines. Yeah, I'm going to draw some lines here, here, here. Oh, some people said horizontal. You could do that too. But I'm going to use vertical for, I guess, a reason I'll name in a minute. And by the way, I don't see any rectangles yet, right? But I guess what would happen is if I started drawing a horizontal line here, and a horizontal line here, and a horizontal line there over to 4, let's say, what I could do is I could add up the areas of these rectangles. And I claim that if I add up the areas of those 3 rectangles, that would be an approximate value for the area under the curve. Let me do that real fast. What's the area of the first black rectangle? Well, we got to do length times width. How long is it? Or how high is it, I should say? 3. And how wide is it? Okay, so this has an area of 3. And this has an area of 4, right? Because it's 1 higher. You guys with me on that? And this has an area of 3. And so that's 10. So I might say, okay, there's an approximate value for the area under the curve. Now, let me ask this. The actual area under the curve, do you think it's more than 10 or less than 10? Me too. Because I see all this space over here, right? I see all that space over there. So what you might try then is you might try filling it up with rectangles also. But you notice when I did this, I deliberately made all the rectangles width 1 to make it real easy to do the computation. You know, some people would say, why don't you draw another rectangle here? Well, you could. But then notice there's little places that I have too much. See that? And then there's little places I have too little. Okay. So I'm going to talk about what area approximation has to do with what are called sums. And yeah, so what I can do is, because this is a parabola, to make the problem easier, let's only consider the area between the lines x equals 0 and x equals 2. Let me do that. And you might say, well, why are you doing that? Well, let me draw the picture, and maybe that'll explain it. Here. Remember our graph looked like this. And what points did it go through? It went through 0, 0, right? And it went through, I think, 1, 3. And it went through what else? 2, 4. So if I only consider the area between the lines x equals 0 and x equals 2, I'm basically finding up to here. Here's the line x equals 2, right? Then what will I be able to do to get the full answer? Just multiply by 2, because we have a lot of symmetry here because it's a parabola. So now the idea is, let's divide this into 4 rectangles. And your book is going to call what I'm doing here the right endpoint method. So what they do is they take the x-axis and they divide it up into, well, this number, 4 intervals. So when you go from 0 to 2, if you want to divide it up into 4 intervals, how big is each interval going to be? A half, right? Because you divide this in half, and then you divide each of those in half, and so you have these 4 points, right? Is this okay? And maybe I'm going to need a calculator here. To make a little of the calculations easier, so let me do that. Here, I'm going to type in, what was it? 4x minus x squared. And because this is such an easy example, if I hit the zoom button, and if I choose choice 6, zoom standard, it's going to give me a real nice graph. Okay? So that's nice. Or maybe what I'll do, if I really want to zoom in and look at it, I'll change the window and make it go from, say, 0 to 2. And make this one go from 0 to 5 or something like that. Okay, so there's the graph, right? From 0 to 2. And now what I can do is I can evaluate some of these values at some of the points here. So I'm going to put in 0.5. And it shows me that when x is 0.5, y is 1.75. And I'm going to need that point. So when I come here, I'm going to put that point there. That is 0.5, 1.75. And then this point here is 1, 3. And that point there is 2, 4. And I guess I also need this point. That point is 1.5, comma, I'm going to use the calculator again to get it. Second, calculate a value 1.5. 3.75. So it's almost at 4. Okay. You guys with me? I have these points. And I'm going to do what's called the right endpoint method. And what that means is, on each interval, when you draw the rectangle as high as the right endpoint. So this first rectangle, from here to here, is going to go how high? 1.75. Right? This rectangle is going to go how high? 3. This rectangle is going to go how high? 3.75. And then the last rectangle is going to go 4. Okay? Now, if I were to compute the areas of these 4 black rectangles, that would give me an estimate of, well, half of the area I want, right? The area from 0 to 2. Would my estimate, what would you say about my estimate? It's too much. It's an overestimate, right? But only little pieces. This piece, this piece, this piece, this piece. Okay? Now, if you want a better estimate, somebody got very clever and said, well, all you have to do is that instead of dividing it into 4 rectangles, what do? Divide it into more. So say you divide it into 40 rectangles. Do you see how that would give you a better estimate? Because when you had the curve, each little rectangle would only have a little bit hanging over. You guys see how that works? Okay? Now, I want to add up the areas of these rectangles. So how do I do it? Well, notice they all have the same width. What's the width? Not anymore. Now the width is 0.5 because I made the delta x. Oh, there it is. What's delta mean? The change in x for each rectangle is smaller. And so all this crazy stuff up here in this formula maybe is starting to make sense now. What you're going to do is you're going to take 0.5, which is my delta x, and multiply by the height, which for the first rectangle was 1.75, right? Plus the next rectangle, if I were to find its area, I guess it would be 3 times 0.5. The next rectangle, if I were to add it up, would be what? Good. 3.75 times 0.5. And then the next rectangle would be 4 times what? 0.5. So all I have to do is add all that up. And I'm going to get an overestimate. I know that. But it'll be an approximation for the area. Now, if you wanted to add all that up, is there any tricks you can do? What's that? A summation? Yeah, we're going to do a summation eventually. That's what this sigma means. It means add. But before I do that, let me just point out, can I do this? And then times what? Does that help? Yeah, it actually does, because if you add it up now, I get 7, 10, 11, 12 and a half times 0.5. Right? And by the way, remember, this is only half of the answer. So what's the whole area according to my approximation using this method? Well, about 12 and a half. What did I get last time that I tried it? I think I got 10. Now 12 and a half is too high, but it's a better approximation than 10. What you saw demonstrated here is called the right endpoint method. Okay? Now, this number 4 here, our book uses the letter n because we're going to divide, in general, the area under curve into n rectangles. So when you guys see that little n there, for us, that's a 4. How many have seen this symbol before, this sigma symbol? Not enough. Okay. This means add from this number to this number. Add from I equals 1 to n. So for us, add I equals 1 to what? Yeah, basically what we're going to do is we're going to add a whole bunch of areas of rectangles. How do you find the area of a rectangle? What did I say is going to be the width? This delta x, that's the width. What's the length of the rectangle, or how tall it is? Well, that's the right endpoint. And the way you get how tall it is you have to you evaluate the function at that endpoint. So this is the height of the rectangle if you want. Height of each rectangle. And the delta xi is the width. So what I hope is going to happen, not yet, but I hope by the end of the class, this formula here is going to make sense to you. I'm plotting the important points again so we can go ahead and do the left endpoint method. I guess this would be, what point is that? 0.5, what was it? I'm going to lose it there. What was it? 1.75? Okay. And then up here we had 1.5 comma 3.75, right? Okay. So there's a sketch of my graph again. And again, I'm only going up to the halfway point, and then I could double the final answer if I want, and that works pretty well. Okay. And we divide it into rectangles again. But what we do now is we use the left endpoint of each of these intervals. Now let's see how that works. Okay. So, get my black ink out again. What I'm going to do is I'm going to draw a rectangle that is an underestimate of the area of the curve. Do you guys see that? And then I'm going to draw a left rectangle here. It's an underestimate of the curve. It's an underestimate of the curve. I guess the last one I don't even draw. So it looks to me like there's going to be more error here because I have a big space here. Is that okay? All right, so let's add up the areas. So now the underestimate would be, okay, well, what's this area? I guess it's 1.75 times 0.5, right? Plus 3 times 0.5 plus 3.75 times 0.5, right? So if you add all that up, again, I could do this trick. Right? If you want, this first one is an area of 0. Okay, the first rectangle. So what do we get? 5.5, 8.5. Okay, so you get about 8.5. This is an underestimate. You get the idea? How do you make it more accurate? More rectangles for more accuracy. Now you might ask, are there other ways you can make it more accurate? And that'll be important later, that question. What's the number of rectangles? N. For us, it was 4. Okay, how many intervals you're dividing it up into? Although I guess the first rectangle ended up being flat because it was at 0. But that doesn't always happen. Okay. Now, we get to an important idea. The area under a curve formula says the following. The area is going to equal, here's an idea from Calc 1. How do you read that? The limit as n approaches infinity. What is n again? What do I mean, the number of rectangles approaches infinity? As you get more and more rectangles, and how do you do that? How do you get more and more rectangles? Well, you have to take your thing from 0 to 2 and divide it up into pieces that are smaller and smaller, right? See, as n goes to infinity, what else is going to happen? I'm going to write down, notice that delta x is going to go to what? 0. Yeah. The width of these things has to go to 0 as n goes to infinity, right? And then you have this beautiful formula. Because remember, these are the widths. And over here, this is the length. So this is the area under a curve. Does that make sense? If you could do an infinite number of rectangles, well, you can't. But as you approach infinity, you're going to approach the area of the curve. And the cool fact, let me skip that. I'll come back to that, is that, and this is not the notation your book used, but it is what I used on the slides, and it's what I've seen in other books. Remember I did the right endpoint method? When I did the right endpoint method, did we have an overestimate or an underestimate in this problem? Overestimate. That was this guy. So I used capital S for that, and capital M I could use if I want. Trying to say, look, these are too big. This is when I did the other endpoint. The left endpoint, I had an underestimate. But the key observation, which mathematicians have done, is that in either case, if you take the limit as n goes to infinity, these two limits are actually going to be equal. You'll get the area of the curve either way, whether you're starting too big and coming down or starting too small and coming up, by just making the number of intervals go to infinity. Okay? Now, back to the slide I skipped. This section is also about something called the definite integral. The definite integral. And there's your formula. Now, by the way, what's the difference between an indefinite integral and a definite integral? Well, symbol-wise, do you see something different? It's these guys, right? You see those things? Little a and little b? Those are called limits of integration. Limits of integration. What do they mean? They mean the following. Well, I'll get to that. I'll get to what they mean in a second. I'm going to put that off. Now, what do you notice over here on the right-hand side? Haven't we seen that before? What is that? Area of what? Area under a curve. See, wait a minute. Go back to the area under the curve formula. We just walked through that makes sense. And now, for some reason, we're going to make up something called the definite integral. And it's the same thing. It's the area under the curve. So in other words, this represents the area under, well, it says under the curve. Under what curve? What's that? Yes, bounded by those two limits. That's right. Under what curve? Well, under the curve f of x. Under the graph of f of x and above the x-axis. So this symbol, because we already know that this is how you find area, this symbol represents the area of the graph of f of x under the graph and above the x-axis. Okay? And then what you're saying is between the lines x equals 0 and, I'm sorry, x equals a, because that's the lower limit, and x equals b. So I guess I'll say this. In the last few slides, we have been approximating what integral? Well, integral from 0 to what? to 2, because remember we chopped it in half. And then what was our function that we were under? I think it was 4x minus x squared, right? Wasn't that it? Dx. Okay? So the definite integral we get as an area under a curve. That's what it is. That's how we want to think of it. And I guess when we come back next time, what we're going to do is we're going to put together ideas from section 1, where you're finding antiderivatives, with ideas from this section, okay, finding area under a curve, and that all comes together in what's called the fundamental theorem of calculus. Okay, that's how it all gets put together. So the fundamental theorem of calculus. What Newton and Leibniz are famous for. So, here it is. A theorem in mathematics is an important fact or idea that mathematicians were able to prove that it works. One thing interesting about mathematics compared to all other disciplines is that you prove everything. If this is true, then that is true. And then if this is true, then that is true. And we get this big chain. And most students, the only place they ever see that is when they take their high school geometry course. I think some of you guys may have done proofs. Some of you may have hated proofs. When I was at Case for my PhD, my PhD advisor, he's a mathematician there, David Singer. His specialty is geometry. And one of the worst math classes he said he ever took, he hated high school geometry. He hated doing proofs. And now he does proofs in geometry for a living. That's what the guy does. Okay? It's not always the most positive experience. The fundamental theorem of calculus was proven separately by Leibniz and Newton. And it's an important fact where there's these two unrelated topics that somehow come together. They were able to put the pieces together here. We're not going to prove it in this class. Okay? If you want that, take Math 2500. Okay? You need to take trigonometry before you do that, I guess. But we can at least tell you the significance of it. You'll be able to see how powerful it is and why it's important, I guess. So here it is written. Suppose that f is continuous on the closed interval AB. Now what's that mean about our function? We talked about that a little bit in Applied Calc 1, so I know some of you know. What's that word continuous mean? No break. You don't lift your pencil. If I draw the graph and I'm moving from left to right, there's no break. There's no place that all of a sudden I have to pick up my pencil and start over again. This is an example of a function that's not continuous right here. Most functions that you will deal with, maybe almost all the functions you will deal with, are continuous. Not all of them. I'll show you one that's not, for sure. We saw them in the last class. But most of them are continuous everywhere, actually. And definitely continuous on an interval, AB. Okay, so you might say if f is nice, a nice function, and suppose capital F is an antiderivative of little f. So I have two functions here, right? I have little f and big F. Kind of like in the problem on the homework, we had little b and big B. Remember that? Little b, I forget what they stood for. Remember that? The problem you guys asked about, 69 or whatever it was? The bankruptcy. Little b was the bankruptcy rate per year. And big B was just the number of bankruptcies. Right? So big B was the antiderivative of the little b. That's on the homework you guys did. Okay. If you have that situation, then here's the beautiful fact. Okay, what does it say? What's this on the left? What kind of integral? That's the definite integral. What does it mean?
Taking the antiderivative of, well, I mean, the whole thing means that you're taking the antiderivative at the second point and subtracting the first point.
Okay, so that's what this side says. This side says, take the antiderivative evaluate it at the endpoints and subtract. That's what the right-hand side says. Take the antiderivative, or integrate. Evaluate it at the endpoints and subtract. That's what the right-hand side says, right? Because big F is the antiderivative. A and B are the endpoints. We're going to subtract them. What is this thing supposed to be again? This is what we just spent time on. This is the area under what? What curve? Little f of x. The area under little f of x between what? Yeah, a and b. X equals a and x equals b. That's what this is. So the fundamental theorem of calculus says, look, if you want to find the area under a curve, take the antiderivative, evaluate it at the endpoints, and subtract, and that does it. And that's pretty remarkable. Why would an antiderivative have anything to do with finding the area? Well, that's what they were able to discover. They discovered it using limits of rectangles. Okay? The rectangles that we worked with in the homework. What they did was they added them up in clever ways and added more and more of them and saw what the limit of that sequence was. And we studied limits when we did derivatives in Applied Calc 1. And when they did the limit, they ended up getting the area. It's kind of cool. Okay, but we're not going to prove it. We are going to do an example. And actually, I'd like to do the example I did last time. This is the example from your notes when we covered the area stuff, right? We had a parabola. And you might remember it goes through 0, 0, and it also goes through 4, 0. And up here it goes through 2, 4, I think. It was a real nice, goes through 1, 3. It was a real nice example where you don't deal with a lot of fractions. I think it goes through 3, 3. So we're trying to find the area under the curve. And when I did it last time, how did I do it? Divided it up into rectangles, and that was an approximate answer. And I think we got the approximate answer of 12.5 after a lot of work. The first time I did it, I think I got 10. Then the other way I did it, I got 12.5. Something like that. Okay, so the fundamental theorem of calculus says all you need to do is first of all figure out big F, the antiderivative. That's why they use this notation, because it's an antiderivative. So let's do that. Let's find the antiderivative. What will we get? Well, the x is going to become an x squared, right? So we get 4x squared, but then what do I have to do? Divide by 2, because when I take the derivative, that 2 I want to cancel, right? Minus, well, the x squared is going to become an x cubed over what? 3. Is that okay? No, that's not okay. Mike say, I don't get that. how do I check to see if I have the right antiderivative? Let's take the derivative of the thing I just got. Of course, I guess another way to write that, which makes it more clear, this is just 2x squared, right? And what's this? 1/3 x cubed, right? Do you see it now? Yeah. So 2 times 2 would give me the 4x, and then the 3 would cancel with the 1/3. Okay? So a lot of times people will write it this way. Is that okay? Oh, I'm going to do something once here, and then never do it again. Never do it again? I thought we always have to do that, right? Plus c. Why did I say I'm never going to do it? It turns out you never have to do it when you have this kind of integral, which is called what? Definite integral. So I'm going to write down this is not necessary for a definite integral. And I'll show you why right now. Let me get a new color, though. Actually, let me erase some of this. Okay. So what we do now, according to the formula, is we take the antiderivative and we evaluate it at B and also at A. And by the way, there's a shorthand way of writing this. A shorthand way for that difference is we'll write capital F of x, and we'll put a line here, and we'll put an A down here, and we'll put a B up there. Not the squiggle like you had for the integral. You're going to have a straight line. Okay? So it's going to be F of B minus F of A is what that means. It's just a shorthand way of writing it. So when I do this problem, this is the antiderivative, right? And then I draw my line. I put a B here, and I put an A there. Okay? So now what you do is everywhere there's an X, you put a B, because that's what F of B means. So let's see. This would be 2b squared minus 1/3 b cubed plus c. That's my F of B. Okay? Minus, what do I put here? 2a squared minus 1/3 a cubed. What would it be? Plus c. Why did I put a's and b's? The fundamental theorem of calculus does have some limitations, okay? Or at least things you might want to worry about. So I want to consider these examples. I'm going to find the integral from 0 to 4 of x squared minus 4x dx. All right, so let's do it. So we integrate. What do we get? When you integrate x squared, that becomes what? 1/3 x cubed. I know it becomes x cubed, and I put the 1/3 out front. Is that okay? How about this? This one becomes minus 2x squared. Very good. If you got that, then you're starting to do this a little faster, right? The x becomes the x squared, and I make this a 2, so when I work it out, I get what I had. I don't need the plus c. All I need to do is draw a line here, put the 0 here, and put the 4 there. What does that mean I'm going to do? What's that?
Insert those values you evaluate for.
Yep. So we're going to insert the values. So we have 1/3 times 4 cubed minus 2 times 4 squared, right? Minus, so that's one of them. That's my F of B. Bless you. And now minus 1/3 times 0 cubed minus 2 times 0 squared. F of A. Of course, F of A here is 0, right? So you end up subtracting 0. That's kind of nice. So let's see, I get 1/3 of 64 minus 2 times 16. So 64 thirds minus 32. Looks to me like that's negative 10.6 repeating. Negative 10 and 2/3, if you work it out. That's the problem. You can't have a negative area. Heather doesn't like that, right? So it's true you cannot have a negative area, but you can have a negative value for an integral. And we have to learn what it means. Okay? So let me show you. Here, I'll go to the calculator. Let me get my calculator back up here. Let me hit the y equals screen. Oh, that's almost right. I don't want 4 minus x squared. Well, first thing I'm going to do is I'm going to do the last example. We have this one, 4x minus x squared. That was my first example I did. And I got positive 10 and 2/3. So let me just insert a little x here. Okay, 4x minus x squared. I'm going to graph it. There's the parabola that we found the area of, right? We found the area under the curve. Now, by the way, I want to show you a cool feature your calculator has. I don't know if you've seen this. Hit the second key, calculate. Look at choice 7. You can integrate a function. It says lower limit. You know what letter they're asking for there? A. What's our A? 0. So I would press 0, enter. Now it says upper limit. And notice it puts a little arrow here. I'm going to put 4, enter. Look, it even colored in the area it found. And it says that the integral of f of x dx is 10 and 2/3. Isn't that nice? Okay, now, back to Heather's question. What's going on when we do x squared minus 4x? We computed the integral and we got the same value but negative, right? And let me not highlight this one. I only want to graph the new function, x squared minus 4x. I'm going to graph it. Ah. So what's the difference? Yeah, it dips below. It's the same picture, but it just flipped over the axis, right? Because we subtracted the other way. Everything's the opposite. And now if I do second calculate the integral, choice 7, and again I'll go from 0 to 4, notice it says that the area is negative. See that? Well, area can't be negative. All they're saying is, when you get a negative value of area, we're saying that the curve is below the x-axis. And so we can think of that as negative area, if you want. That's how the integral will treat it. So it's good to know about that. Especially when you get to an example like this other one here. Here. This one. We're going to go from negative 3 to 3. Let's integrate x cubed dx. Okay. Go ahead and work that one out. Okay, so I'm going to help you working this out. When you integrate x cubed, what do you get? 1/4 x to the 4th. And you were evaluating from negative 3 to positive 3, right? So I get 1/4 of 3 to the 4th power, and I subtract 1/4 of -3 to the 4th power. By the way, what happens to when you do -3 to the 4th power? What happens there? It becomes positive, so you get positive 81. Same thing as that when you have positive 3. When you subtract this all, what's it going to equal? Do you see how it has to equal 0? And you might say, well, why would that happen? You're not going to get 0 area, are you? Well, again, let's look at the calculator, and that might help us. I'm going to turn this on, go back to the y equals screen, clear some of these out, and I'm going to put in x cubed. X, how do you put in cubed? There's this caret key above the divide. The caret in computer languages means exponent. Okay? So now what I do, let me integrate it. So we'll graph it. There's your, maybe already you know what's happening. Do you see why we're going to get 0? Because when you integrate, choice 7, from -3 to 3, half of the area is below the x-axis, half the area is above. It's the same amount of area. They cancel each other out. And so your book is going to call it the net area. The net area is 0. Not the gross area. The gross area would be add these two areas together. Okay. So if I actually wanted to know how much area that was, how would you do it? Right. Or maybe from 0 to 3, because you want it to be positive. If you go from -3 to 0, you're going to be below, it'll be negative. But yes, that's exactly right. Just do part of it and multiply. You guys follow that? Good. Problem 62 says, in part B, we're going to do this integral. All right? But before we do that, let me start with part A. Part A says, find the x-intercepts of the function. How do you do that? How do you find the x-intercepts of the function? You find the zeros of the function. Those are the x-intercepts. Yeah. Because why? Because to be an x-intercept, you have to have a y value of 0. Right? And so we're trying to find all the places where this function could equal 0. The function is y equals x cubed minus 2x squared minus 3x. And I noticed someone said factor, because when you're trying to figure out how do I get it to equal 0, well, you factor this thing. Right? So we're trying to solve 0 equals x cubed minus 2x squared minus 3x. How would you guys factor that if you were starting to factor it? All right, here's your algebra skills at work now, right? I always tell people, you want to learn algebra? Take calculus. Okay, now what do I do with this x squared minus 2x minus 3? That factors into x minus 3 times x plus 1, I think, works. And so I get 3 x-intercepts. I get x equals 0, x equals 3, x equals -1. Okay? So now I can actually sketch a graph of this thing. The graph of this function would look like this. It goes through -1 comma 0. It goes through 0, 0. And it goes through 3, 0. And so it goes kind of like this. There we go. So that's your function. It's a cubic function. Okay. So now, part B might make more sense to you. Part B says, let's integrate from x equals -2 to x equals +3. Let's integrate. Of course, when you integrate, that's going to be what the book calls the net area. Because what's going to happen? Parts of it are going to be negative, and then parts of it are going to be positive. Do you guys see that? All right, but let's work out what this is. So we can compute this value of the integral, and we get, oh, what do? Okay, let's see if you can integrate. I'll pause it while you work that out. All right, so what do we have here? Let's see. 1/4 x to the 4th minus 2/3 x cubed minus 3/2 x squared. Right? Is that okay? This is easy now, huh? So I'm evaluating all this stuff from -2 to +3. You work this out, you're going to get plenty of practice with your algebra, I guess. All right, let's see where we're at. 1/4, 3 to the 4th power is 81, minus 2/3 of 27, minus 3/2 of 9. Okay, now here you have to watch your negative signs, right? I like to personally leave this thing in parentheses for a while. So -2 to the 4th power would be 16. Minus 2/3. What about -2 to the 3rd power? That's your -8. Minus 3/2. And this is +4. Okay. Okay, so I get 81/4 minus 18 minus 27/2. Now, -4, and then minus, minus, minus. That's another negative. So minus 16/3 minus a -6. So that's +6. Wow. Work that out. Then you got it. So part B. Oh, let's see. Some of you may have resorted to the calculator by now, right? So let's see. Here's 80 and a 4th minus, so that's 20 and a 4th minus 13 and 2/4. Wow. Here, I'll hit the calculator from this point on. I think just doing this is just fine at this point. So we get that value? -14.583 repeating. Huh? Okay. So there's your part B. Now part C says, hey guys, I really want to know how much area this is in red. So my question is, how do you do it?
You can break it up to 3 different sections.
Yeah.
And make the
That's right.
Use absolute value.
You could also absolute value. You could also absolute value. That's right. I mean, basically, I want to integrate, let's see, from -2 to what? To -1 f of x dx. And I want to add what I get from 1 to 0 f of x dx. Oh yes, from -1 to 0. I'm splitting it up into pieces. Oh, and when I go from -2 to -1, that integral is going to be negative, right? So you can either, as you said, take the absolute value, or as you said, you could put a negative sign in front. And then I'm going to want to integrate from 0 to 3. So if I subtract what I get when I integrate from 0 to 3, that'll also do it. Okay, so that's the method for doing part C. Here, let me show you how to do it on the calculator, let's say. Okay, so maybe what I should have done from the beginning is let's put the function in here. So it's x cubed minus 2x squared minus 3x, okay? And I'll sketch a quick graph. There's my cubic function, like I showed you. And now, just to show you that we were on the right track, if I were to integrate from -2 to +3, so you could check your answers real quick. There's my -14.58. So we did that one right. But now if I say, what's the actual area? Well, choice 7 again. Let's go from -2 to, what do we say? -1. And I got -3.91. So what I want to do, I want to add 3.91, right? So here, let me running out of colors. Let's go back to blue. So I want to take 3.91. And now I'll go back to the calculator. And let's integrate again. This time from -1 to 0. So there's 0.583. Repeating if you want. And then, almost done, we're going to integrate, what would it be? I guess from 0 to 3. And that's going to be a negative value, -11.25. So I'll add on 11.25. So if I add all that up, that's the answer. There's a 3. 9 and 5 is 14. Carry 1. 7. 15.74 approximately is the area of those 3 shaded regions added together. Does that make sense? Right? In the last example, we said, here's what the rule says. Suppose f is a continuous function on AB. That's what we had. We had a cubic function. That's continuous. What you're allowed to do is you're allowed to split up your integral at any point you want between A and B. And so we do that especially at zeros, because then you're going to change from negative values of the integral to positive values of the integral. Does that make sense? Okay. I have one last mysterious example that I want us to do. So I want to integrate this function by hand. Do this one by hand. Mike, try it by hand first, then we'll use the calculator. See if you guys can integrate these. What's the trick? What do I do? I go from negative 3 to 3. What would I write? X to the negative 2 dx, right? What do you mean use a line?
So you have to use LN when you get the...
Oh, ln, natural log. We will get to that. Not for this problem. If you had 1 over x, you'll have to use natural log. And we'll get to that next time. No, this one, if you write it this way, it's going to work. Because now, think about what I do now. What function would I want that's the antiderivative of x to the negative 2? X to the negative 1, right? That's one higher exponent. But what do I have to put out front so that when I take the derivative I get this? Yeah, you need a negative out front so that when I take the derivative I'll get x to the negative 2. Is that okay? Laura, is that okay? Yeah. Okay. So now I'm here, and I'm evaluating from negative 3 to 3. Okay, so we're going to test your algebra skills big time here. See if you get this or not. All right, so what do? I plug in 3. And by the way, before I even start, what does x to the negative first power mean? Yeah, let's just write this as negative 1 over x that we're evaluating from negative 3 to positive 3. That might be easier. Okay, so I get negative 1 over 3 minus negative 1 over negative 3. You got to be careful with your negative signs here. So I tried to really make it big so you could see where all my negative signs are. And I also wrote 1 over x to try and get rid of one of the negative signs. Is this okay? Who's with me? Nick, you all right with here? Yeah? Okay. So now what? Well, let's write this out. I guess I get negative 1/3. And then would this be plus or minus? Well, it depends how many negatives there are. Let's say negative, 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 minus another 1/3. So I get negative 2/3. There's my integral. I don't like that. You know why I don't like that? What's not continuous? That's the problem. The reason I don't like it is because, you guys, this function here, f of x is 1 over x squared. Can that function ever be negative? Can you ever get an output that's negative? When you put in your inputs, aren't they always positive? Because you're squaring, right? So this function is above the x-axis. So how, if it's always above the x-axis, how would I get a negative integral? I just told you you get negative when you're below the x-axis. See what I'm saying? But Mike actually hit upon the problem here. This function is not continuous somewhere. Where is it not continuous? It's not continuous at 0. If you were to graph this function, the graph looks kind of like this. And at 0, you know what you have? It's called asymptote. That's right. And if you have an asymptote there, you may have all kinds of problems going on. Because, well, what am I doing? I'm graphing from negative 3 to positive 3. But look at all this area. You might have an infinite number, right? It can go as high as you want. And you might say, well, does that even make sense anymore? So yeah, we have a problem. So to do this problem, let me just take a big magic marker, and you should too. and say, this is not correct. Because 1 over x squared is not continuous at x equals 0. Okay? Now, we will learn how to deal with it. We will learn how to deal with it. The idea is going to be rewrite it like this. But this is no good either right now. Why is this no good? Because you can't even put a 0 in for the function. Even the antiderivative, 1 over x, you can't put a 0 in. So we're not ready for it yet. This is what's called an improper integral. When you get endpoints that, well, do things like this. But we'll get to those later. What's that? You will take a limit, yeah. You will take a limit.